In today's class and video, we are going to perform an experiment to determine the wavelength of maximum absorption for colored solutions. So we'll start by looking at what wavelength of maximum absorption is. So the wavelength of maximum absorption is the wavelength at which a substance absorbs the most light, and it is also known as absorption maximum wavelength or lambda maximum, which is normally written as this. And one key thing that we have to note in this experiment is that the wavelength of maximum absorption is determined by recording the absorbance values of a color solution over a range of wavelengths, say 400 nanometer to 700 nanometer, with intervals of 5 or 10 or 20 or even 50 or even 100, depending on what you want. So now let's take a look at this graph over here. And the graph over here shows the absorption spectrum for a third sample at different wavelengths. So these are the wavelength 360, 443, 471, and 502 nanometers, with the wavelength 471 nanometer being the wavelength at which there is a maximum absorption of light, and this can be seen by the peaks produced in the graph. So now let us look at the materials needed for this experiment. The first is the UVV spectrophotometer. We also have the methylene blue, methyl orange, the unknown mixture of the two indicators, and cuvettes. So now let's take a look at these keynotes before we start with the experiment. So first, students will be provided with methylene blue, methyl orange, and the unknown mixture of the two indicators with a known concentration of 100 milligrams per liter. And two, students will be required to prepare a working concentration of 10 milligrams per liter from each 100 milligrams per liter indicator given. And this happens to be the methylene blue, the methyl orange, and the unknown mixture. So now let us just take an example and look at how to prepare a working concentration solution of 10 milligrams per liter of the methylene blue from the standard solution 100 milligrams per liter in final volume of 20 ml. So obviously we'll use the equation C1V1 equals C2V2. So where our V1 happens to be the volume of the standard indicator needed to prepare the working solution. C1 happens to be the initial concentration of our standard. C2 happens to be the final concentration that we want to prepare. And V2 is the final volume of the indicator. So from the question, we can see that our C1 is 100 milligrams per liter, C2 is 10 milligrams per liter, our V2 is 20 ml. So we will have to look for our V1. So if you are to make V1 the subject from this equation, you will get V1 to be equal to C2V2 or divided by C1. And if you are to substitute these values into the equation, we will get V1 to be equal to 2 ml. So what it means is that if you want to prepare the 10 milligrams per liter in 20 ml for our working solution, we will have to aliquot 2 ml of the standard solution, which is the 100 milligrams per liter methylene blue, into a 20 ml volumetric flask and top up with distilled water to the mark. So now let's look at our test protocol. So the first is to zero the spectrophotometer using distilled water as blank. 2 is to determine the absorbance of each indicator at the following wavelength between 400 nanometer to 700 nanometer with intervals of 20. 3 is to plot a graph of the absorbance values obtained against the respective wavelength. And 4 is to determine the wavelength that gives the maximum absorbance for each of the indicator. So now this is just an assumed table of result after performing our experiment, and this table shows the various wavelength that we use and the absorbance values for the methyl orange, the methylene blue, and the mixture, which happens to be a combination of the equal volumes of the methyl orange and the methylene blue of the same concentration. Now, so if we should take a look at our table over here, we can see that the maximum absorption for the methyl orange occurred at the wavelength of 460 nanometer with the absorbance value of 0.716, and that of the methylene blue also occurred at 660 nanometer with the absorbance value of 1.537. And one interesting thing that we also have to note here is that the mixture will have two wavelengths at which there will be a maximum absorption because of the presence of the methyl orange and the methylene blue. So at a wavelength of 460 nanometer, it is expected that the methyl orange in the mixture will be absorbed. So with the value of 0.363 over here, and also at a wavelength of 660 nanometer, the methylene blue in the mixture will also have its maximum absorption with a value of 0.746. So now let us look at the graph showing the absorption spectrum for our test samples, and this happens to be the indicators. So this is our methyl orange shown over here. This is also our methylene blue, and this is also the unknown mixture over here. And one key thing that we have to note is that from the graph, the wavelength of maximum absorption for the methylene blue is at 660 nanometer as shown here, and that of the methyl orange is also at 460 nanometer. And also it can be seen that the unknown mixture has two wavelengths at which there is a maximum absorption, and this is as a result of the presence of the methylene blue and the methyl orange. So we can see that at the wavelength of 460 nanometer, the methyl orange in the indicator will have its maximum absorption over here, and also at the wavelength of 660 nanometer, the methylene blue in the mixture will also have its maximum absorption over here. So this is just the nature of graph that we are expecting. So now let's see some questions, and I'll advise you just try your hands on them. 1. Why is it important to use colored solutions in determining the wavelength of maximum absorption? 2. Why is it advisable to use the wavelength of maximum absorption when measuring absorbance to determine the concentration of a compound? And 3. What is the difference between wavelength and absorbance? And 4. State 5 ways the cuvette needs to be handled to ensure a more accurate result. And 5. What does an absorption spectrum graph shows? And 6. Why is distilled water used as plan? So I would just advise you just take your time and go through these questions and solve them before you come into the lab.